Hello everyone and welcome to another remote sensing lecture video. And in this video we're going to pick up where we left off talking about the 4 dimensions of remote sensing. We talked about spatial, spectral, temporal, and radiometric. So what I want to do in this video is tackle the first one on our list, the spatial dimension. And it's important here to understand that you'll oftentimes see me refer to it and see textbooks refer to it as spatial resolution. And in specific in ArcGIS Pro, you'll see them use the term cell size. So all three of these terms, spatial dimension, spatial resolution, and cell size, are used more or less interchangeably, especially at this level. So what I want to do here is before we go into any examples or any deeper explanation, I just want to throw out a quick one-sentence definition. So hopefully this is going to be slightly reviewed because we've kind of talked about the spatial resolution already when we talked about calculating areas of pixels. But spatial resolution refers to the size of one pixel, right? The size of one pixel. So that's just a quick one sentence definition. But what I want to do is I want to just sort of reiterate what that means, and I want to look at some examples and explain some trade-offs and some reasons why you might care about spatial resolution. So what we're going to do is we're going to go over here and we're going to start a new area in our notes called spatial resolution. And what I want to start doing is I want to start by just reiterating that definition, but I want to be a little bit more specific, right? So we're going to start by saying spatial resolution or spatial dimension, spatial resolution, spatial resolution, cell size, right? I'm going to put all these here because you're going to see all these terms appearing in the textbook and the notes, and cell size especially appearing in software, right? So these three terms are all basically the same thing. For our purposes, these are the same thing. And what we're talking about is we're talking about the length, right? The length of one side of a single pixel. Right, so we've sort of built upon that previous definition to be explicit in saying it's the length of one side of a single pixel. And I want to just quickly underline the word one side here because invariably people will make mistakes and assume that it's the area, but it's not. It's the length of one side. So just to sort of reiterate this connection to the remote sensing data structure, right? We have the pixel here. So this is a pixel. This is a pixel from our remote sensing data structure. And when we're talking about spatial resolution, right, we're talking about this right here, this length of one side. This is the spatial resolution. And it's important to realize that there's nothing special about this bottom here, right? We've sort of defined our pixels to be squares. So the spatial resolution could be referring to this side or this side, it doesn't matter. And if you remember back to how to calculate the area, right, the area of this pixel is just the spatial resolution times the spatial resolution. And hopefully that's a review for you. But what I want to do now is I want to look at some examples of why we care about spatial resolution. And I'm going to reiterate what spatial resolution means as we go through these things. So let's go down here, and in this case we have 3 different data sets. So I'm going from decreasing spatial resolution, right? So the larger the number, right? We say that through decreasing spatial resolution. So we're going to do this just to make sure that we're all clear on what's happening, right? We are going from this way to here, right? We are decreasing spatial resolution. This is a decreasing spatial resolution. larger number sorry, let me raise my bad handwriting here. Larger number means lower resolution. And these are, take it, just assume here, these are the same area in all three of these images. And what you can see is that over here, in this image, this ortho image, we have a spatial resolution of 5 feet. So just to sort of reiterate what that means here, we have our pixel, right? And that means that this length right here, this length is 0.5. Actually, it's 1.5 feet, right? NAPE has 1 meter or 3.82 feet. And just to make sure that everything's consistent, this length right here is going to be 3.28 feet. And all the way over here to Landsat, which is the largest spatial resolution that we have. I'm just going to slide this over really quickly so I can actually write properly. Right, so Landsat, right, this has a spatial resolution of 98.43 feet. And again, we have a single pixel here. And we're saying that this length right here, this is the 98.43 feet, right? So what I want you to pay attention to is that as we decrease our spatial resolution, right, as our cell size gets larger, right, going from 0.5 feet, so half a foot, to just over 3 feet, to over 90 feet, you can already see that we're losing detail, right? We're losing the ability to perceive smaller objects in the image. And at this particular scale, right, looking at this particular zoom level, right, comparing ortho to NAPE might not seem like that big of a difference. So what I want to do is I want to just pan down here a little bit. So we've zoomed in a little bit here. We've zoomed in on the parking lot. We've zoomed in on this parking lot right here. And you'll see that in this image, right, in the ortho image at 0.5 feet, we can resolve individual cars. But if you look at the NAPE image, you can't resolve individual cars anymore. The cars start to blend together. And I didn't even bother putting the Landsat image down here because it would have only been 1 or 2 pixels. So just to sort of reiterate the point here is that the larger the number, right, the larger that spatial resolution or the larger that cell size is, the lower the spatial resolution and you have a decreased ability to resolve fine scale features. So now you might be asking yourself, okay, well, why wouldn't we want everything to be this 5 foot, right? This 5 foot, or sorry, half a foot, 0.5 foot, right? Why wouldn't we want all of our imagery to be that? Why do we even have Landsat? Right? I want to take a minute to sort of talk about that because I think that's a really important discussion point, especially as we advance technology and we advance hardware, is to sort of talk about the question of why not always use ultra high spatial resolution. Imagery, right? That's a valid question, right? Why wouldn't we always want to use what you may perceive as the best? Now, there are a lot of sort of nuanced answers to this question involving things like spatial scale of analysis, but really in my mind, there's one key reason, well, 2 key reasons. And the first is really this trade-off, right? There's a trade-off between the cell size of an individual pixel and the area that the image covers. Right, there's a trade-off between cell size and total area covered. Now, as you progress through some of the labs that are associated with this, you'll start to see this trade-off in a more clear manner. But for now, just believe me when I say that the general idea is the smaller the cell size, right, the smaller the area covered. Right, so that's the big trade-off here, is that as you decrease the size of the cells, as you shrink those pixels so you can resolve finer and finer detail, you shrink the overall area that the image covers. So you end up covering less area. So if you want to cover a lot of area, you might be saying, okay, well, that's fine. I'll just use more images, right? I'll take multiple images and they're taking different neighboring images and I'll put them together. And you certainly can do that. That is completely valid. But there are some issues that go along with that in terms of we'll talk about radiometric accuracy at a later date. But when you start using multiple images, you do two things. One, you increase the likelihood of having issues with data quality. And two, and this is more important, is you end up with a large data volume. And that's really the second key thing here, is this trade-off between cell size and total area covered. And then the second thing here is the trade-off between cell size and data volume. Right, and in this case, as you decrease cell size, right, as our pixels get smaller and smaller, you have a tendency to increase your data volume. Now, what do I mean when I say increasing data volume? What I mean by that is if you take a Landsat image, right, if we scroll back up here and we compare these, and we compare these three images again, right, even though they cover the same aerial extent, right, I've clipped them so they all cover the same aerial extent, this Landsat image takes up much less disk space, right? We're talking about megabytes, gigabytes, that kind of thing, right? This Landsat image takes up much less disk space than this ortho image does. And so you can imagine as we scale out beyond a small portion of Farmingdale's campus to say maybe the entirety of Long Island, you can imagine how quickly the data volume adds up. And something like an ortho image might become unwieldily large, even with modern computing technology, right? It's maybe more data than most computers can handle. And there are ways around that, but from a remote sensing analysis perspective, right, there's definitely that trade-off between data volume and spatial resolution. And especially when you're looking at larger areas, you really need to be aware that you might not be able to use ortho imagery, for example, because it would just be too large of a file size. So again, just to reiterate here, why we don't always want to use ultra-high spatial resolution imagery. One, because as you decrease the cell size, you typically tend to shrink the area that's covered by a single image. And then as you decrease the cell size, you tend to increase the data volume. So hopefully this made sense. Hopefully you can see the difference when we increase and decrease spatial resolution, and hopefully you understand why we don't automatically always jump for the highest spatial resolution imagery possible. So as always, if you have any questions, I encourage you to pause, go back, rewatch the parts of the video that you're confused on, and as always, please reach out. Thank you.